Welcome to the Breakthrough Broadcast, a podcast about innovative STEM solutions to real-world problems. From emerging technologies to practical research, Drew Reck explores how science, engineering, and bold thinking are shaping the future.
I'm Drew, and this episode is about how microbes are eating our plastic waste and turning it into something useful. Picture a conveyor belt inside a recycling plant. Plastic moves past sorting machines, past human workers with gloves and masks, past scanners that try to guess if each piece is a bottle, a cup, or a clamshell. The process feels industrial and familiar. What most people don't realize is that the system barely works. The world produces hundreds of millions of tons of plastic each year, but only a sliver of it actually gets recycled. The rest piles up in landfills, drifts out to sea, or breaks apart into fragments so small that they slip into soil, food, and the water we drink. The story of plastic pollution has become so familiar that it's easy to tune out. That changed when scientists began to discover organisms that treat plastic the way they treat fallen leaves or wood. They break it apart. They digest it. They turn it into something useful. Suddenly, plastic waste looked less as a permanent scar on the planet and more like a pile of future raw material. The idea feels fake. Microbes that eat soda bottles and turn them into chemicals for jet fuel, fabrics, or food additives don't match the mental picture that most people have of recycling. Yet research labs and pilot plants around the world are already proving that it can work. Researchers are redesigning enzymes, rewriting microbial pathways, and building reactors that act more like living factories than industrial shredders. This episode explores the science behind that shift. So, how do microbes break apart plastic at the molecular level? Plastic molecules are long chains built from repeating units. They're strong, flexible, and chemically stable, which is why they became so popular. That stability also makes them stubborn when they are tried to break apart. Microbes don't chew on plastic directly. Instead, enzymes released by the cells start the process. These enzymes clip the long chains into shorter fragments. Once the fragments are small enough to cross the cell membrane, the microbe pulls them from inside and begins turning them into energy or chemical building blocks. The most important breakthroughs in recent years involve enzymes that target PET, one of the most common plastics in bottles and packaging. Early PET-eating enzymes worked slowly and required warm conditions. Researchers learned how to tune their shape at the atomic level so that they latch onto the chain more tightly and release the fragments more efficiently. Directed evolution tools sped this up. Enzymes get mutated, tested, screened, and improved over and over again. Some of the latest versions take hours to dismantle a bottle. The entire chain becomes a soup of familiar chemicals that once came from petroleum, but now come from waste. Scientists use structural biology tools to understand each part of the process. X-ray technology freezes the enzyme in place so researchers can see how each piece works. Molecular dynamics simulations show what might happen next between snapshots in time of this X-ray. Knowledge like this helps guide the next round of tweaks. The goal is a fast, stable enzyme that can survive real-world conditions. Once these enzymes chop plastic into small molecules, microbes have to decide what to do with the pieces. Wild organisms tend to break them down slowly and create a mix of products. That approach is far too messy for large-scale use. The field changed when researchers started building metabolic funnels inside these enzymes. This means that the enzymes reroute the fragments through a single metabolic pathway that leads one product instead of many. Imagine a bacteria that receives one single PET fragment. Instead of sending it through several competing branches, the cells direct the molecule through a controlled sequence of reactions. Every step is chosen for yield and efficiency. Some strains now produce a single compound with very little waste. This solves a major industrial challenge. The more predictable the product, the easier it becomes to integrate biological recycling into supply chains. Scientists also use these microbes to make valuable materials. Some engineered strains convert plastic fragments into precursors for nylon. Others turn them into aromatic chemicals used in coatings, flavorings, or pigments. A few have even been tuned to create the branched hydrocarbons that resemble aviation fuel. This unlocks an entirely new idea. Plastic waste becomes a feedstock for manufacturing rather than an environmental burden. To maintain stability, researchers introduce genetic circuits that keep the cells from drifting too far from their intended function. They also modify the cell membrane to handle unusual byproducts. Each change makes the microbe more robust for industrial use. In terms of integrating this recycling technology into the global economy, one of the most exciting aspects is the potential to reshape the way industries think about raw materials. Unlike traditional recycling, which often produces low-quality outputs or makes plastics of limited value, biological systems generate precise chemical products that are immediately useful. Again, PET fragments can be converted into high-quality fibers or into things used for adhesives or flavorings. This creates a direct pathway from waste to industrial-grade product. Large manufacturers are beginning to take notice. Some pilot programs are partnering with beverage companies to recover bottles that would otherwise end up in landfills. Instead of simply melting them down, these plastics feed into microbial reactors that produce constant outputs, which can return to the same production lines and help these soda companies. This creates a circular economy where the same material repeatedly flows through production and recycling, reducing dependence on new petroleum. Logistics and supply chains play a crucial role. Biological recycling systems can be modular and decentralized, meaning urban centers, industrial parks, or remote facilities can operate small bioreactors tailored to local waste streams. Sensors and AI monitoring help these systems match throughput to demand, ensuring that plastic fragments never sit idle for long periods. Economically, this approach offers flexibility. High-value chemical products can offset operational costs, while governments and companies explore incentives for circular materials, like those soda bottles. By linking microbial recycling directly to industrial production, the technology moves beyond lab-scale novelty and toward an integrated solution. Industrial waste streams are rarely clean, and they need to be for this process to work. They contain layers, dyes, dirt, and several types of plastic blended together. Traditional recycling requires sorting each type because melting temperatures and chemical properties vary widely. Microbial solutions avoid this step through a clever trick. Instead of a single engineered organism, researchers combine several species together to cooperate. Each species specializes in a different bond type or type of plastic. One microbe might handle PET, another tackles polyurethane, and a third works on polystyrene. They live together in the same reactor and pass byproducts back and forth. The process is similar to a natural ecosystem. Cooperation increases, and each organism focuses on its own niche. Some consortia include helper microbes that stabilize pH or remove small toxins that would slow the others down. These systems are carefully controlled. Researchers track population balance with genetic markers and tune conditions like temperature, oxygen, and nutrient flow. Some teams use sensors that monitor chemical signatures to detect when one species becomes stressed or overwhelmed. Automated feedback adjusts conditions in real time. This technology allows a messy stream of mixed plastic to be fed into a reactor without sorting and still produce clean outputs. Again, plastic recycling rarely happens under ideal lab conditions. Waste piles carry food residue, dirt, dyes, and oils. Temperature can swing, pH levels can drift. Older enzymes lose activity under these conditions. Newer ones tolerate extremes far better. Researchers accomplish this by altering loops on the surface of the enzyme, strengthening the bonds that hold it together, or adding amino acids that can increase stability in the microbial system. Machine learning models predict which changes might help before the enzyme is even built. That cuts down on trial and error. Scientists can now design variants that remain active at low temperatures or stay stable in salty environments. This is crucial for outdoor bioreactors or floating systems that treat ocean plastic in the ocean. One of the most impressive enzymes works with almost no heat. It starts digesting plastic at ambient temperatures, which saves an enormous amount of energy and cost. Fortunately, there are lots of new designs that support living systems. Bioreactors for microbial recycling do not look like typical chemical plants. They need to keep millions of cells alive, active, and balanced. This means precise control of oxygen, temperature, and nutrient delivery. Modern reactors rely on arrays of sensors that read conditions each second. One breakthrough is real-time metabolic monitoring. Sensors detect how quickly the microbes consume plastic fragments and how their internal chemistry shifts. Software adjusts flow rates, temperature, and mixing immediately. This tight control doubles efficiency in some pilots. Another innovation involves layered reactors. Plastic enters at the top, and enzymes begin to soften it. Midway through the system, microbes take over and convert the fragments. At the bottom, chemical extraction units collect the final product. Each layer is tuned for a different task. The design mimics a natural digestive system, where each region carries out a specific piece of the job. Researchers are also testing bioreactors that use sheets coated with enzymes instead of liquid cultures. These sheets will sit on top of the waste and use sunlight to power the reactions. They require less electricity, which makes them attractive for lots of use cases. Scientists are realizing that the best solution might not wait for recycling. It starts during manufacturing. Some new plastics include tiny chemical handles that make it easier for microbes or enzymes to grip them later. The plastic behaves normally during use, but it breaks apart quickly in specialized recycling systems. This approach doesn't solve all waste, but it helps create a closed loop for new products. Essentially, we can design plastics so that it's easier to recycle. Another idea involves designing these plastics that blend biodegradable components into conventional plastics in a controlled way. These components act as access points for enzymes to deconstruct this plastic. They weaken the chain enough for microbes to finish the job, even if this conventional plastic is sturdy. Materials science look at how these blends affect strength, transparency, and cost. The goal is a plastic that looks and performs like the products consumers expect, while offering a clear path, a cheaper path, into the manufacturing cycle once it reaches a recycling plant. Another big application of this is marine microbial systems to deconstruct ocean plastic. Plastic in the ocean spreads across huge distances. Research groups are focused on safe, contained approaches to break it down without harming the marine life. One method uses floating barriers that corral microplastics into controlled zones. Inside those zones, engineering marine microbes attach to the particles, secrete enzymes, and break the plastic into harmless pieces. The microbes remain in place because the barriers confine them. This prevents uncontrolled movement through the ocean. Despite rapid progress, biological plastic recycling faces real limitations. One major challenge is the scale. Lab results look impressive, yet global plastic production is enormous. Moving from small reactors to giant industrial sites is not simple. Enzymes that perform well in controlled studies can behave differently when dealing with large volumes of dirty waste. Contaminants like dyes, oils, or mixed additives can slow the process and reduce yields. Another limitation involves feedstock diversity. There are many types of plastic, and each has its own chemistry. PET has been the main focus because it breaks down into valuable molecules. Other plastics require different enzymes or different microbes, many of which we don't have the technology for yet. This creates logistical hurdles for facilities that receive unpredictable waste streams. Consortia help solve this, but they require tight oversight and sometimes struggle with difficult plastics. Cost is another large concern. Chemical recycling methods can run at high temperatures and process huge amounts quickly, although they often produce mixed outputs. Biological recycling saves energy and produces cleaner products. The reactors, sensors, and strains need careful maintenance. The economics depend on the market value of the products created by the microbes. If the product is valuable, the process works. If the market shifts, profitability changes, and the process might not be as effective. Environmental risk must also be considered. Engineered organisms are designed with safety switches, but careful monitoring is essential. Most proposed systems operate in sealed, indoor facilities where escape is unlikely. Outdoor marine systems need strong containment. Researchers continue to assess safety features before deployment. Finally, Some plastics simply do not have clear biological pathways yet. Strong polymers used in construction or specialized firms resist current enzymes. Research is exploring new approaches, but these materials may require chemical pretreatment or entirely new strategies. The future of microbial plastic recycling looks hopeful. The field moves quickly because it blends biology, chemistry, computation, and material science. Progress in one area accelerates progress in the others. One clear direction involves pairing biological recycling with chemical pretreatment. A gentle chemical step softens stubborn plastics so enzymes can finish the job. This opens the door to a broader range of materials. The combination allows facilities to process waste streams that once seemed impossible to handle. AI will also influence enzyme design even more strongly. Models learn from thousands of successful or failed mutations and predict which combinations produce the fastest or most stable enzymes. Researchers can leapfrog years of testing by designing promising candidates directly on the computer before building them. Microbial factories will become more specialized. Cells will be tuned not only for speed, but also for stability and product quality. Some strains will handle tough fragments, others will polish intermediates, and some will synthesize high-value chemicals. These networks of engineered microbes will behave like coordinated teams. Another major direction involves integrating biological recycling into existing waste infrastructure. Sorting plants might divert certain streams to enzyme-based systems while sending other materials to mechanical or chemical processes. The result is a hybrid network where each type of recycling handles the material it works best with. There's also potential for decentralized recycling. Small bioreactors powered by solar panels or waste heat could remove remote communities or industrial sites and allow them to recycle despite not being near any reactors. On the materials side, manufacturers will create plastics designed for future digestion. This does not mean fragile products. Instead, it means plastics with controlled weak points that activate during recycling but remain strong during use. This could shift the entire life cycle of many consumer goods. Marine solutions will continue to evolve as well. Contained cleanup zones might expand near coastlines. Sensors could track plastic movement and direct floating barriers to new locations. Microbes will digest the captured fragments without drifting away. The most exciting part of this future is the possibility that plastic stops being considered permanent waste. Instead, it's a renewable resource that cycles through production, use, biological recovery, and eventually manufacturing again. The planet gains breathing room, and society discovers a new industrial ecosystem built around living machines. Frankly, plastic pollution feels overwhelming. People picture mountains of bottles, beaches littered with fragments, and ocean currents carrying floating trash across entire basins. The issue has felt the same for decades because the solutions haven't really changed. Yet biology is rewriting that story. Scientists are now treating plastic not as a relic of petroleum chemistry, but as a new kind of feedstock for biology. Enzymes can bite into it. Microbes can burn it. Entire reactors can run like ecosystems instead of furnaces. The science is young and ambitious. Researchers are not satisfied with slow digestion or limited outputs. They want fast products, resilient solutions, and clean chemical products that slip back into industry. They want systems that work on messy waste streams and survive harsh environments. Most of all, they want a world where plastic isn't causing problems in the ocean or in big landfills. There are challenges. Scaling is difficult. Economics must line up with environmental goals. Safety needs attention, but even so, the pace of progress hints at something larger. Biological recycling may not erase the plastic problem on its own, but it gives society a powerful new tool. It reshapes how we think about waste and turns on a global burden into a source of raw material for the future.
Thanks for tuning in to the Breakthrough broadcast. If today's conversation sparked a new idea, share the episode and follow the show wherever you listen. Got a question, idea, or breakthrough of your own? Reach out at breakthroughbroadcastconnect@gmail.com. Until next time, keep questioning, keep building, and don't wait for the future. Help create it.